Hello, I'm Rylan. Welcome to a novel approach to calculating orbital mechanics with machine learning. In 1609, Johannes Kepler proposed the two-body problem, which describes the motion of two gravitationally relevant bodies around each other. In 1687, Isaac Newton discovered an analytical solution to the problem, now known as Newton's law of universal gravitation. Of course, the universe has many more than two bodies in it, so this problem is only useful for certain isolated situations. Therefore, the three-body problem was proposed. This question describes the motions of three gravitationally relevant bodies around each other, visualized here. No analytical solution has been discovered for this type of problem. Three-body problems can also be generalized into the n-body problem, which describes the motion of n gravitationally relevant bodies around each other. These problems more closely reflect the real world. Approximate solutions to these problems have been proposed, most notable being numerical integration. With this method, the forces on each body in the system being studied are calculated at intervals of time using Newton's law of universal gravitation. The n-body system is considered to be a set of two-body systems. The forces calculated in one interval are then used to estimate the motions of the bodies for a short period of time until they are once again recalculated in the next interval. This approach has several downsides. Calculating the forces at frequent intervals is computationally expensive, requiring large amounts of time and computing power. And this computing power results in a solution that becomes progressively less accurate as the simulation advances in time due to the estimations required by the approach. I explored the feasibility of applying machine learning to solving these problems. Previous studies have found machine learning to be successful in solving partial differential equations similar to those that are used in solving n-body problems. Instead of calculating forces and positions step by step like classical solutions, the model identifies patterns. A primary advantage here would be time. The machine learning model could predict trajectories in a tiny fraction of the time it would take a program employing classical methods. Computation time would also be much more consistent and therefore predictable. My goal then was set: develop a machine learning-based program that could match a classical solution-based program in terms of accuracy while doing so at a much faster speed. I started by establishing parameters. A previous study by researchers at the University of Edinburgh set out to estimate the trajectories of three bodies, each with an equal starting mass and no initial velocity. To parallel more realistic scenarios, I decided to expand this to four bodies with unique masses and starting velocities. Like the Edinburgh study, however, I calculated the trajectories in a 2D plane. After carefully considering the advantages of calculating in a three-dimensional space, I determined that calculating in a two-dimensional plane would still reflect realistic trajectories. As you can see here, the planets in our solar system orbit the Sun in a coplanar manner, on what is known as the invariable plane. The same can be said for nearly every other solar system we can observe. Limiting the project to two dimensions also reduces the number of variables that must be accounted for, which was a significant advantage due to the limited computing power I had access to. The next step was developing the solution. First, I needed a dataset on which to train the machine learning model. I got to work developing a program that employed numerical integration to estimate the trajectories of gravitational bodies in the four-body systems I was studying. I adapted Newton's law of gravitation for this purpose. The formula can be transformed into a differential equation, translated into code, and then plugged into an ordinary differential equation solver. Using object-oriented programming principles, I designed a base program in Python that could then be built upon later in the project in other programs. I developed the first of these programs to create visual representations such as this one, as well as to debug the base program. However, training machine learning models requires copious amounts of data. In the case of this project, a data set of 10,000 solved four-body problems was desired. Generating solutions to each of these problems by hand was not feasible, so I developed another program that randomly generates starting conditions and then solves the trajectories of the four-body system using the aforementioned base solver. It outputs two NumPy arrays of floating point values that can be later imported into a script to train the machine learning model. One of these arrays includes the initial conditions and times for each problem, and the other array contains the calculated trajectories. The next step was training the model. Using Google Colaboratory, I wrote a Python script that imported the previously created dataset, compiled a model, and trained the model on that dataset. I went through several iterations designing the model. I started with a model similar to that used in the Edinburgh study, but was unsatisfied with the results. I altered the model structure, introducing regularizers, normalization and dropout layers, and adjusted the optimizer function, eventually testing 9 unique variations. Because each alteration required several hours of training, I was limited by time in how many alterations I could test. I did achieve some improvement, however. I found the most optimal model structure to be a 10-layer model. The first 9 layers contained 256 nodes each, and the last output layer contained 8 nodes. Each node employed a rectified linear activation function, and the model as a whole was compiled with an adaptive moment estimation optimizer function and a mean squared error loss function. After training the model, it had to be tested. This could not be done in the Google Collaboratory workspace, so the model's weights were exported in a checkpoint file. Then, I wrote a custom program to evaluate accuracy. The program solved a 4-body problem with both the classical method and the machine learning method, and then calculated how far from the classical solution the machine learning solution diverged, at 6 time intervals. Each solution outputs an array of floating point values that represent the positions of each gravitational body at the specified time. With these values, the Pythagorean theorem was calculated to determine the divergence of the 2 solutions. It is this divergence that is graphed here against time. Greater divergence indicates less accuracy in the machine learning model, and as can be seen here, the model was not perfectly accurate, but does demonstrate some amount of success. As time increases, accuracy decreases. Other variations of the machine learning model demonstrated similar behavior, with the exception of the dropout and fusion models, which showcase a resistance to the trend of increasing time and decreasing accuracy. This may be a route to explore to improve the accuracy of the model. One question I had was whether the machine learning solution was just guessing numbers, or if it had actually gained an understanding of the intricacies of gravitational motion. I attempted a traditional statistical analysis of the data and found no statistically significant difference between the output of the classical solution and the output of the machine learning solution. I wasn't satisfied with this conclusion, though, as I felt it yielded an incomplete analysis of the data. Therefore, I inspected the motion of the center of mass. If the machine learning model recognized the law of conservation of momentum, then I could conclude that the model had in fact gained an understanding of the gravitational motion. Graphed here is the accuracy of the model at calculating the center of mass of the 4-body system. Like before, less divergence indicates greater accuracy, and in this case, the model had minimal divergence and has come to understand the concept of gravitational motion. Accuracy is only half the project, though. Speed is the other half. In this, the machine learning model proved to be dramatically faster than the classical solution, which, on average, was 40 times slower. The machine learning solution was also able to solve problems in a consistent amount of time, whereas the classical solution varied widely in calculation time. In conclusion, this study has proven that machine learning-based solutions are capable of efficiently solving complex 4-body problems. While additional work is needed to increase the accuracy of these solutions, I've proven that they are capable of recognizing the patterns in the partial differential equations used to solve 4-body problems classically. In coming to these conclusions, I made a few assumptions. I assumed that the classical solution program I developed was completely accurate. Reality is that without a supercomputer, some amount of error is inherent in the trajectories calculated by the program. Even with a computer, the nature of numerical integration is that it will never yield an exact answer. I also assumed that modeling the gravitational motion in 2 dimensions would sufficiently replicate real-world phenomena. As previously noted, this assumption was justified through data. Broadly speaking, this study's major limitation was access to computing power. With more power, a larger, more realistic dataset could be within reach. More variations of the machine learning model could be explored, trained, and tested, thus improving accuracy. That is where the future comes in. This project has proven a concept. Machine learning can be applied to the realm of gravitational motion. With further development, we could see more efficient plotting of celestial motion. New spaceflight maneuvers could be revealed, such as more complex variations of Hohmann transfers and gravity-assisted trajectories. Humanity is destined to explore space. With this project, we can plot a course to get there. Thank you.